All right.
Where do you get your beaver slides or whatever you're using? They're so cool.
These?
Yeah.
Oh, I just make them. What?
Is it PowerPoint or Beamer?
This is actually PowerPoint,
Okay.
but sometimes I do both. Sometimes I'll use PowerPoint and then I'll kind of pull, like I'll actually go into Adobe Professional and I'll pull in parts from Beamer because sometimes you can't do certain mathematical things in PowerPoint. It's not a very powerful program in that respect, but it's still pretty good. I think some of the transitional quality and things like that is still quite good in PowerPoint. Well, if I had to pick two mathematicians to kind of get excited about, one would be Euler and the other would be Archimedes. And there's actually this kind of interesting question in my mind as to who is actually more prolific. Because Archimedes just did not have the same kind of mathematical tools that others did. Now, I mean, as we'll see, Archimedes lived, before there was really a whole lot of sophistication. Of course, he was in the Euclidean era, so their mathematical proof and things like that had been somewhat formalized, but there's still just these long, painful ways of saying things that we no longer really have to contend with. So one just wonders what might have happened. And actually in this lecture, we may or may not end up seeing it, but there's a recording at the end of this math historian who kind of does a lot of talks about the sorts of things Archimedes did. And incidentally, we're still translating a lot of the things that he did, not just translating into English, but trying to understand what the English is even saying, because you'll see that some of the language ends up being fairly clunky. Okay, that's the stuff of math historians. They sometimes aren't just translating from one language into another, but from English into modern mathematical language. And it's astounding to see the sorts of things that Archimedes did. Okay, and by the way, I mean, it's pretty remarkable. If you look at kind of ancient renderings of Archimedes, they all look fairly similar. So that's probably a fairly accurate sculpture rendering of Archimedes. This is about his area of a circle formula, okay? All right, so again, he's born in the 3rd century BC in Syracuse. Now, I know there's a lot of talk in modern days about how the ancients were so quaint that they thought that the earth was flat and things like that. That's simply not true. The Greeks and most of the ancients were well aware that the earth was round, and they knew it had to be because of some of the measurements that they would attempt to get, like between cities. They knew that there was something off, and a lot of that was aided in astronomy and kind of geometric reasoning, having a hard time translating from flat surfaces to apparently the curved surface of the earth. Somewhat stunning to me that in the light of that, it took them so long to realize that the parallel postulate could be kind of cast out in favor of a different kind of geometry, namely spherical geometry, one where the lines are actually finite. But Archimedes was obsessed with kind of like planetary motion and celestial mechanics. Of course, none of that really got super formalized until much later on with people like Isaac Newton. But most of what we know about Archimedes comes from the writings of Plutarch. He wrote this thing called Life of Marcellus, and we'll hear more about him very soon. And also Archimedes wrote a lot of letters to the school in Alexandria. And so there's a lot of information in there as well. So he was in Egypt as a boy. That's where Alexandria was. By the way, I mean, that really was kind of a hub of academic activity for a very, very long time. There's a very famous library in Alexandria, which very tragically, a lot of archival material was lost during one of the many plunderings of that area. And trained in the Euclidean tradition. Here's a little passage on page 85 to just illustrate the sort of individual that Archimedes was. He clearly was a strange guy. So his awesome mathematical talent was augmented by an ability to devote himself single-mindedly to any problem at hand in extraordinary periods of intense, focused concentration. At such times, the more mundane concerns of life were simply ignored. We learn from Plutarch that Archimedes would, quote, forget his food, neglect his person to such a degree that when he was occasionally carried by absolute violence to bathe or have his body anointed by oil, he used to trace geometric figures in the ashes of the fire and diagrams in the oil on his body, being in a state of entire preoccupation and, in the truest sense, divine possession with his love and delight in science. End quote. This passage portrays the stereotypically absent-minded mathematician, not to mention one to whom cleanliness was next to irrelevant. Of course, the most famous absent-minded story concerns the crown of King Hieron of Syracuse. Now, this is interesting. The king, suspicious that his goldsmith had substituted some lesser alloy for the crown's gold, asked Archimedes to determine its true composition. And as the story goes, Archimedes wrestled with the problem until one day, during what must have been one of his rare baths, he hit upon the solution. Jumping from the bath, he ran through the streets of Syracuse, shouting, "Eureka! Eureka!" Unfortunately, so absorbed was he in his wonderful discovery that he forgot to don his toga. What the townspeople thought at seeing their fellow citizen running stark naked in their midst is impossible to say. So that is Archimedes. You've probably heard about the Eureka idea, but basically he figured out a way to measure density, which was amazing, and it worked. And I think he actually did show, I think it says in here, he actually did show that the guy had swindled the king. So he wrote a treatise called On Floating Bodies, which was basically kind of a large scale treatment of, what he had discerned as far as density was concerned, but also just kind of the general principle of trying to utilize water for physical purposes, whatever that might be. He invented something called Archimedean screw, which was like an ancient water pump, the likes of which had not been known before his time. Seems like they were exclusively beholden to things like aqueducts and whatnot. And he came up with this screw to actually move water up in a very controlled way. And it's actually still used today. You can look it up on the internet. He was obsessed with pulleys, levers, optics, and really developed some of the core ideas that we still use today. He wasn't really wrong about anything, which is a fairly rare thing for the ancients, for sure, even when it comes to physics. It's an amazing guy. So this is kind of a famous event in the life of Archimedes. So Marcellus, who was the subject of the life of Marcellus, written by Plutarch, is a very famous Roman general. And he invaded Syracuse. And actually, this is something that we kind of freak out about today, but back then also, a lot of the ideas that that Archimedes came up with were immediately turned into various weapons of war of extreme brutality. And they were developed into things that actually kept the Romans at bay for years, specifically at Syracuse. There was a great feast that happened at one point after a long siege, and they kind of let their guard down, and that was the moment of destruction. I was actually going to read this passage right here. It's pretty interesting stuff. So, in what follows, we continue to quote liberally from Plutarch's Life of Marcellus, written by the great Roman biographer almost 3 centuries after the fact. While it was Marcellus about whom Plutarch was ostensibly writing, his admiration for Archimedes was quite evident. These writings provide us with an intriguing and certainly a very colorful account of Archimedes in action. Quote, Marcellus moved with his whole army to Syracuse, and encamping near the walls sent ambassadors into the city. End quote. When the Syracusans refused to surrender, Marcellus opened his attack on the city walls, both on the land side with his troops and on the ocean side with 60 heavily armed galleys. Marcellus was counting on, quote, the abundance and magnificence of his preparations and on his own previous glory, end quote. But he would prove no match for Archimedes and his diabolical war machines. According to Plutarch, the Roman legions marched to the city walls, believing themselves to be invincible. Quote from Plutarch. But when Archimedes began to ply his engines, he at once shot against the land forces all sorts of missile weapons and immense masses of stone that came down with incredible noise and violence, against which no man could stand, for they knocked down those upon whom they fell in heaps, breaking all their ranks and files. And the Roman naval forces fared no better, for huge poles thrust out from the walls over the ships and sunk some by the great weights which they let down from on high upon them. Others they lifted up into the air by an iron hand or beak, and when they had drawn them up by the prow and set them on end upon the poop deck, they plunged them to the bottom of the sea, or else the ships drawn by engines within and whirled about were dashed against the steep rocks that stood jutting out under the walls with great destruction of the soldiers that were aboard them, end quote. So he's obviously losing lots of levers and pulleys and whatnot. Such destruction, related Plutarch, was, quote, a dreadful thing to behold, end quote, and one is inclined to agree. Under the circumstances, Marcellus thought it prudent to retreat. He withdrew both land and naval forces to regroup, and holding a council of war, the Romans decided upon a night assault, and the expectation that Archimedes' devilish weapons could be useless if the attackers slipped too close to the walls under the cover of darkness. Again, the Romans had an unpleasant surprise. The diligent Archimedes had arranged his devices for just such an eventuality, and no sooner had the Romans crept up close upon the fortifications that, quote, stones came tumbling down perpendicularly upon their heads, and as it were, the whole wall shot out arrows at them, end quote. In response, the terrified Romans again retreated, only to come under attack from Archimedes' longer range weapons, an attack that, quote, inflicted a great slaughter among them, end quote. By this time, the vaunted Roman legions, quote, seeing that indefinite mischief overwhelmed them from no visible means, began to think they were fighting with the gods, end quote. It is perhaps an understatement to say that Marcellus had a serious morale problem. He demanded of his shaken troops a renewed courage to continue the assault, but the previously invincible Romans wanted no more of it. On the contrary, the soldiers, quote, if did but see a little rope or a piece of wood from the wall, instantly crying out that there it was again. Archimedes was about to let fly some engine at them. They turned their backs and fled, end quote. Knowing that discretion is the better part of valor, Marcellus chose to abandon the direct assault. And instead, trying to starve the trapped Syracusans into surrender, the Romans began a long siege of the city. Time passed with no change in the disposition of forces. Then, during the great feast to Diana, City inhabitants, given up entirely to wine and sport, became careless about guarding a section of the wall, and the opportunistic Romans saw their chance. Their armies broke through the lightly guarded section, poured into the city in a vicious and destructive mood. Marcellus, surveying the beautiful town, is said to have wept in anticipation of the havoc that his men were sure to wreak. Indeed, history records that the Romans treated Syracuse no less harshly than they would treat Carthage some 66 years later. But it was the death of Archimedes that brought Marcellus his greatest sorrow, for he had come to respect his gifted antagonist. According to Plutarch, quote, as fate would have it, intent upon working out some problem by a diagram, and having fixed his mind alike and his eyes upon the subject of his speculation, Archimedes never noticed the incursion of the Romans, nor that the city was taken. In this transport of study and contemplation, a soldier, unexpectedly coming up to him, commanded him to follow to Marcellus, which he declining to do before he had worked out his problem to a demonstration. The soldier, enraged, drew his sword and ran him through, end quote. Thus ended the life of Archimedes. He died as he lived, lost in thought about his beloved mathematics. We can regard him either as a martyr to his research or as a victim of his own preoccupied mind. In any case, mathematicians may come and mathematicians may go, but no other has had an end quite like this. For all of Archimedes' great weapons, for all of his practical inventions, his true love was pure math. His levers and pulleys and catapults were mere trifles compared with the beautiful theorems he discovered. And in fact, I mean, it goes on to say in here that Marcellus was so upset with this soldier right here in this picture, apparently, that ran Archimedes through, that he made an example of him and did some damage. Actually, that's in another history book, but it's not in this one. Interesting stuff. So let's talk about the circular area prior to Archimedes. So what the Greeks knew was that if you took a circle's circumference and divided by its diameter, you always got the same number, which is merely an expression of similarity. So every circle is similar to every other circle because you're just blowing it up by some constant, yes? Therefore, if I divide one length respective to the circle by another length, you're always going to get the same constant because every circle is a blown up version of every other circle or shrunk down version. Don't you see? Yeah. So they knew that C over D was some kind of constant, and because they're Greek, they called it pi. Okay. Proposition book 12, number 2 of Euclid's Elements says that the ratio of the circular area to the square of the diameter, the ratio of circular area to the square of the diameter is a constant. Okay. But here's the thing. Nobody really knew what that constant was. Okay. So the area, and here's another thing that was known prior to Archimedes. If you have a regular polygon, let me actually just draw a picture of this so that we can see what's going on here. You have a regular polygon like this hexagon right here. Okay. The area of this regular polygon is 1/2 h times q. All right, so what is h? H is the so-called apothem. Okay. Okay, so I don't know, here's like an S right here. And don't you know that, so like if this is the length of this side right here, S, yes? This right here is the so-called apothem, H, okay? What is the area of that triangle? I'm not trying to insult your intelligence, but what is the area of that triangle right there? 1/2 SH, right? So the area of that triangle is equal to 1/2 h times s. And don't you see that if you add up all those triangles, what are you going to end up getting? Like if I add up all those triangles, you're going to have the same apothem everywhere, aren't you? And it's just going to be 1/2 the apothem times the side all the way around. If you add those together, you're going to be able to factor out 1/2 times the apothem, don't you see? And so you're going to end up with 1/2 the apothem times the entire perimeter, because you just add together all the sides of the regular polygon. Yeah? Make sense? Okay. Any questions on that? So that's where the formula 1/2 HQ comes from, where H is the so-called apothem. They also knew, and this is just kind of obvious, all right, that if you take an inscribed, respectively circumscribed polygon, then the area would be less if it's an inscribed polygon in a circle, or more if it's a circumscribed one, than that of a circle, regardless of how many sides it had. Isn't that sort of obvious? Yes? Okay, but that was sort of a critical element of what we're about to see here. Okay, so that's basically what they knew. They knew that the ratio of a circle's area to the square of its diameter was a constant. They knew this formula for the area of a regular polygon. And they knew about this inscription and circumscription of regular polygons, or just ordinary polygons, in circles, and the relationship between the areas of the two. That it's smaller in one case and bigger in another case. Okay. Measurement of a circle. Okay, the area of any circle is equal to a right angle triangle in which the one of the sides about the right angle is equal to the radius, and the other of the circumference of the circle. So, I mean, what in the world? Can you believe that this is the way they used to have to say things, right? So here's a circle of radius r, okay, and circumference c. And this is Archimedes' proposition here. What he's saying is if you take a right triangle, okay, and one of the legs is of length r and the other one is of length c, then what is the area of this thing going to be given by? Well, it's 1/2 RC. So, and this is the area of the circle also. So this is equal to the area of this triangle as well. It's 1/2 RC. And let's just see if that's the case. I mean, you guys know what the circumference formula is, don't you? What is that? 2 pi r? Okay, so interestingly, what we end up with here is 2's canceling, and you get pi r squared. Yeah. So Archimedes, for whatever reason, he like stated this in terms of a triangle. It was a fairly common thing to do because everybody, like anybody who had any brains, knew that what the area of a triangle was, especially a right angle triangle. Yeah. So that's what he's saying. Make sense? So the statement of this is exactly what we need to get the formula for the area of a circle. All right. So here's what Archimedes did. Starts with two figures, a circle with radius r, circumference c, and a right triangle, like what I just drew, yeah, with base c and height r. The area of the circle he calls A, right? So the area of the circle is called A. So this is the area of the circle. T is the area of that triangle that we just drew. And he has to show that they're the same. Does that make sense? Because it's easy to compute. Well, I mean, what he wants to show is the area of the circle is just 1/2 radius times circumference, basically. Yeah. Now, to prove that those two are the same, he's going to do a double reductio ad absurdum. What does that mean? What is reductio ad absurdum? Reduced to an absurdity, which means contradiction proof. Okay. It's a common proof technique that the Greeks all knew and loved. Okay. All right. Case one. Suppose, okay, remember which of these are which. We use T very strategically because it reminds you of triangles, yes? Okay, so you have this area of this circle and you have the area of this triangle. Circle, both of which have, well, the circle has radius r and circumference c. The triangle has height r and base length c. It's a right triangle, yes? Archimedes knew that by inscribing a square within his circle and repeatedly bisecting it, he could create a regular polygon with area z. So in other words, okay, so he's inscribing a square within his circle here. Okay, so here's this circle. He inscribes a square, then he uses this, you guys know Greeks like to kind of use their instruments for various purposes, yes? And then he would bisect the side of the square and then get a regular octagon, isn't that right? So what was 4 points would now be 8 points. And then he could just bisect away and keep constructing more and more sides to a regular polygon that would get ever and ever and ever closer from the inside to this circle. So I mean, I don't know, I'll just draw, oops, I just erased stuff, sorry. So here's our circle. And he does something like this, all right? So I'm just going to do a hexagon. But he could, he could go a lot further than this. And so what he's saying is, this thing has area A, and this thing right here has area Z. Yes? And if A is greater than T, then of course A minus T is greater than 0. So that's kind of like our epsilon, if you will. Yes? And so what he's saying is, I am going to continually bisect these sides until I come up from the inside and end up with something that is so incredibly close to the area of the circle that the area of the circle minus this inscribed, or inscribed thing is smaller than this epsilon. Does that make sense? And by the way, this would still have been positive, would it not? Yeah, because we've inscribed this thing. Don't you see? So, all right, and I don't know why Archimedes decided to do it this way. They were sort of clumsy with algebra, but he actually adds z plus t minus a to both sides. To us, we just literally say, listen, cancel the a and move t to the other side and then z to the other side. Don't you see? You get that t is less than z. Yes. Okay. All right. That's interesting. But this is an inscribed polygon. Therefore, the perimeter of the polygon X, or of the polygon Q, or the area of this thing is Z, right? The polygon Q, or the perimeter is Q, sorry, what am I saying? Yes, is less than the circumference, yes? So like if I take the circumference of this thing, and Q is the circumference of this guy that we've gotten right here, you know that Q is less than C, correct? Yeah? Because it's inscribed. And its apothem is less than the radius, correct? So look at the apothem of this thing. Here's the apothem. And clearly that's less than the radius. Don't you see? Yeah? It's inscribed. So apothem is less than the radius. How interesting. But what do you know the area, what do you know that the area is? Z is equal to 1/2 h times q. This is something the Greeks would have known, right? But h is less than r. And q is less than c, right? Therefore, 1/2 hq is less than 1/2 rc. But after all, that is the area of the triangle. So don't you see what the contradiction is? Up here, we concluded that t was less than z, but down here, we just got that t is greater than z. So clearly that's a contradiction. Yeah? Make sense? Okay. By the way, I just want to remind you, like, I don't care about like all of the historical details that I give necessarily, but these proofs are so amazing. I do think that you should like know them. Okay. So far what have we seen? We saw Hippocrates' quadrature of the moon. We saw the Euclid's proof of the infinitude of the primes. We saw that in class, actually. We saw Euclid's proof of the Pythagorean theorem, and today we're seeing Archimedes' proof of the formula for circular area. So the conclusion of case one, by the way, is that a greater than t is not possible. We did that by inscribing a regular polygon with enough sides. All right. So what about the second part? Okay, remember, so over here, we did t greater than a. Now we do, here we did a greater than t. Now we're gonna do t greater than a. Yeah? Which means that t minus a is positive. So the triangle minus the circular area is positive. Now what we're gonna do is we're gonna circumscribe about the circle. Okay, so here's the circle right here. I'm just going to do something really stupid. I'm just going to draw a square. Okay. So you circumscribe something. Okay. And once again, this is like A, and the area of this thing is Z. Okay. Circumscribe about the circle a regular polygon with area z that exceeds the circle by no more than t minus a, because after all, t minus a is positive, yes? Okay. So in other words, we're going to make the difference between z and a smaller than this epsilon, yeah? So we're going to have z minus a less than t minus a, and of course, both of these are greater than 0. And then, of course, once again, we can cancel these guys. Look how easy this is. And you just get that z is less than t. Yeah? So the area of z is less than the triangle. But what about the apothem in this case? That's interesting. Let's think about what the apothem here is in this case. Wouldn't the apothem in this case actually, because all of the sides are going to be tangent to the circle because they're regular, are going to be, all of the sides are going to be tangent to the circle at precisely the right point where the apothem is going to actually go out and touch that thing, yes? So actually H, the apothem, is equal to R in this case, okay? What about the perimeter Q? Okay, so Z is the area, Q is the perimeter. How does the perimeter compare to the circumference? Well, it's greater, yes? Q is greater than C. So Z, which is the area of the regular polygon, is equal to 1/2 apothem times perimeter. H and R are the same, so we replace H by R, but Q is strictly bigger than C. So we get that Z is greater than T. So Z is less than T and greater than T at the same time. Impossible. Okay? And that's it. I think that's a pretty cool proof. Yeah? He just used some very basic tools that hopefully make a fair amount of sense to you. Any questions on that? Yeah.
What was the strict definition of an apothem again?
The apothem is basically if you have any regular polygon. So I don't know, here's a regular polygon, like a square, okay? Like if, and I split the regular polygon into a bunch of triangles, the apothem is basically the height of each one of these triangles. Does that make sense? Mm-hmm. So it's kind of like the perpendicular radius out to a side. Yeah? Other questions? Isn't that a neat proof? I think that's pretty neat. So I already said this, but you know that A is equal to the area with circles, the area of that triangle, which is 1/2 the height times the base. The height was radius, the base was circumference. You plug in what you know, and the Greeks would have actually known that C was equal to pi times D. They knew that was true. That's how they defined pi. Did you know they don't have to prove the formula for circumference? Because pi is by definition the common ratio of circumference to diameter. Does that make sense? It's just by similarity. Okay. So that's kind of interesting. One time I actually, I had someone, they were trying to see if I like knew how to teach or something. I was taking this teaching class at Ohio State when I was in grad school. I had someone say, how would you explain to a junior higher, like, why the order of operations are what they are? And I sat there and thought for like 5 minutes. I'm going, PIMDOS. She said, yes, but how would you explain it? And then I was like, oh no. Then I went home. I was just disappointed in myself. And then all of a sudden it dawned on me, it's just because we all agreed that those were the order of operations. Like, we didn't have to do that, but we all have to be able to agree so that we can go to opposite sides of the room and come up with the same thing. You do need parentheses in order to like, override the order of operations if necessary, but we could just as well have all agreed to do another one. It's a similar thing here. Like if I said, hey, prove that the formula for a circle is C equal pi times D, you would say, pi is defined as the ratio of the circumference to the diameter, and all circles are similar. I guess that is more of a proof than the other thing. But yeah, it's like by definition. Okay, so here's some interesting things. Archimedes flat out estimated what pi was by kind of circumscribing and inscribing various polygons and then measuring very carefully. And he actually got that it's less than 3 1/7, but greater than 3 10/71. I don't know if you have a calculator, but I think that means he's probably accurate to like at least 1 decimal place at this point. I think that you might mess up in the hundreds position. Does somebody have a calculator? See, isn't it funny that we're all math people and we never have calculators?
Okay, so 1 divided by 7 is 0.1428.
Okay. So he's accurate to the second. What about the lower bound?
10 divided by 71 is 0.1408.
So he's accurate to within 2 decimal places. That's fairly impressive, especially he didn't have any. So look at this. He made a regular 96 gon. Okay, and at each step he actually had to approximate square roots, obviously. So it's pretty impressive. Okay. Here's a little brief history of pi. Did you know that somebody want to look up First King? You guys better have Bibles on you though.
It's expensive to read.
One of the first known references or estimates of pi actually is in the Bible. I don't know if you knew that or not. Look up 1 Kings 7:23. There's a description of something called the sea, which was basically kind of a huge washing vessel out in the temple courts. What does it say, Matthew? 1 Kings 7:23.
Then he made the sea of cast metal. It was round, 10 cubits from brim to brim, and 5 cubits high, and a line of 30 cubits measured its circumference.
So 10 cubits brim to brim. Okay, 30 cubits around. So what's the circumference divided by the diameter according to that estimate? 3. People might say, oh, but listen, I mean, you're measuring, who knows how thick that brim was? Do you know what I'm saying? There's all sorts of things that could be happening there. Okay, that's a pretty good estimate. Archimedes came up with this one. Ptolemy, it took about 400 years to usurp Archimedes. Chu Shun Chi in 480, 300 years after that. Aryabhata, who was a famous Arab mathematician. Bhaskara, Al-Kashi. This is during the kind of Islamic expansion. This sort of stuff is happening. Francois Vieti, very famous French mathematician. Adrian Anthonizum, Adrian von Reumann, Ludolf van Keulen, Willebrord Snell, Greenberger. This is the lots ever better approximations for pi using more like algebraic techniques. Okay. John Wallis, 1650, sounding a little bit more English, if you will. 1671 was James Gregory, and then Isaac Newton just blew everybody away. And then people, because he of course invented the calculus, which gave him tools that nobody else had before him, really. It took 30 years or so for Abraham Sharp to usurp him, and then John Macon, and then Delagny, and then William Outred, and then Isaac Barrow, who was actually a contemporary of Isaac Newton's, and then David Gregory, John Etienne Montucla. Then there was a collaborative effort by the French Academy of Sciences, Johann Heinrich, Comte de Buffon, Adrien Marie Legendre. You probably heard Legendre before. Then after Legendre, it took a long time for someone to beat it. And that was Rutherford. Okay, Zacharias Days, Rutherford again, William Shanks, F. Lindemann. You ever heard of Lindemann? Well, in real variables, maybe you'll hear about that eventually. Orr, and then Ferguson. Okay, that was 30 or 42 years after Orr. A group called ENIAC, which was kind of like they were starting to use computing to help them approximate pi. And then ENIAC again in 65. And there are certain people who just kind of took this on as personal projects, like Galud twice, and then the Japanese mathematicians Miyoshi and Nakayama, 1981, Bailey in 86, etc. And now it's like nobody cares anymore because Mathematica can give you any degree of precision that you want. Mathematica has infinite precision. So everybody stopped at that point. Now they all look for primes. One of his most famous writings was something called On the Sphere and the Cylinder. And it was the thing he was most proud of. That was the writing that he was most intrigued with. There's an incredible video that I will kind of leave for you to watch that shows the method by which he actually computed the volume of a sphere. And the way that he did it was fairly remarkable. He actually used kind of a balance, if you have a pivot point on a balance, then the weight times the length away from the actual pivot point on the balance, they have to be the same in order to balance perfectly. And he basically used that along with like cones and spheres to actually compute the volume of a sphere. What he did is he kind of balanced some spheres and put some cones on one side, did some stuff. And it took us, only about 2,300 years to figure out what the heck he was talking about. And now that we have, it's fairly amazing. And so there's this little video where that happens. Well, here, actually, I think it's right here is where that video is. Any sphere is equal to 4 times the cone, which has its base equal to the greatest circle in the sphere, its height equal to the radius of the sphere. Well, what does that mean? You can kind of figure, you can write out what it is, just various volume things, and you'll realize you can do a little bit of algebra and actually solve for the volume of a sphere when you do it. We don't really have time to watch it right now, but I would encourage you to go watch this video. It's actually in Canvas. It's incredible. And he does similar things actually with the surface area of a sphere, which is this one right here. The surface of any sphere is equal to 4 times the greatest circle in it. That's pretty easy to translate. You look at the greatest circle that's in the sphere of radius r, which is like, what's the area of that? Pi r squared, and then 4 times that is the surface area. The way he proved that is amazing. He actually did it the same way we just did the formula for the area of a circle, except what he did is he actually stuck the sphere inside of these like cut off frustra of cones. He figured out what the surface area of these frustra of cones were, and he built these frustra of cones on top of each other, and he ends up with some kind of circumscribed shape that consists of frustra of cones. Frustrum of a cone is like you take a cone and you hack off the pointy part. And so he basically put a bunch of those on the outside of a sphere, and it's an amazing thing. The same guy who does this video over here also has a video on this proposition as well. Kind of shows some renderings of what it is that Archimedes was talking about. And Archimedes never really drew pictures. He would just write. And you're like, what is he talking about? Okay. But he does reductio ad absurdum using the method, which was the method that Archimedes called it the method. It was the method of exhaustion, which is approximating things from the inside or the outside and doing it in a limiting way. Don't you see that's kind of what we were doing with the area of a circle? Archimedes was doing calculus before calculus was around. In fact, thousands of years before. Look at this crazy thing. Surface of any right circular cylinder, excluding the bases, is equal to a circle whose radius is a mean proportional between the side of the cylinder and the diameter of the base. That's the sort of thing that you have to contend with when you read through what Archimedes is doing. That's why we're still figuring out what he did. Okay. Well, what it really means is that the lateral surface of a cylinder of height h and radius r is equal to the area of a circle with radius x, where x is determined by the following ratio equation, right? And if you kind of mess around with that, you figure out that you do get the proper formula that you want. So this is kind of an interesting last little tidbit. His favorite result of all was that the volume and the surface area of the cylinder, the volume and the surface area of a cylinder is half again as large as the spheres. Okay, so what does that mean? Help me out here. The volume of the cylinder, okay, and the surface area of the cylinder is 1.5 times as big as that of the spheres, okay? And so what he does, and what he's talking about is a cylinder that has a sphere on the inside of it, kind of like, I think I had a picture back here as well. See this guy right here? Okay, so what he's doing is he's relating the volume and surface area of a sphere to that of the cylinder. He was so excited about that he actually demanded that on his tomb, something like this be put there to adorn it. The fact that the surface area and volume are in ratio 3:2, the cylinder to the sphere. And if you kind of zoom in on this picture, I've done it several times before. If you Google the picture of Archimedes' tomb, you'll always see this, and somewhere in here, there actually is something that looks like this shape, like over the door or something like that. Okay. So it's a pretty cool thing for sure. Any questions? Again, I would commend that video to you. I think that would be a super helpful thing for you, but Archimedes was a remarkable guy. And maybe I'll read the passage about what happened to that soldier at the beginning of class next time. All right, have a good weekend.